All right, everyone. Today we are learning about section 11.2, the properties of power series. Power series are pretty much the namesake of all of chapter 11. And we're going to go ahead and begin our discussion by recalling something back from whenever we studied series. So, first of all, recall the geometric series. We remember that in chapter 10, the geometric series, when we defined a to be equal to 1, which is what this series over here is, the sum from k equals 0 to infinity of r to the k is equal to 1 over 1 minus r. Okay? And this only occurs, of course, if the absolute value of r is less than 1. So, it's a small change to consider replacing this real number r with a variable x. Okay, so if we instead were to write this now as the sum from k equals 0 to infinity of x to the k, this would now be 1 over 1 minus x if the absolute value of x is less than 1. So it may not seem like it, but we've actually just done something pretty remarkable. The idea here is that some functions can be represented as an infinite sum of powers of x. In particular, what we have essentially shown so far is that this function, 1 over 1 minus x, this is just some function, is equal to the sum from k equals 0 to infinity of x to the k. Or we could write that as 1 plus x squared plus x cubed plus x to the fourth. So if we were to do that infinitely many times, these two functions would actually be equal to each other. And one thing that you might actually notice is that this function here, if you were to try and find its Taylor approximation, its Taylor polynomial, for degree 1, it would be this guy. For degree 2 Taylor polynomials, it would be that guy. So let me actually label these. This would be P1, this would be P2, and then if we were to keep going, it would be this thing here would be P3. And so what we have essentially done is we have extended this Taylor polynomial infinitely. And the main conclusion here is that some functions can be represented by power series. And to give you a formal definition of a power series, let's go here. The power series is an infinite series of the form sum from k equals 0 to infinity of ck times x to the k. So ck here, these are just constants, some sort of number that depends on k. A constant that depends on k. Or it might not depend on k. And then x to the k, x is a variable, and k, of course, is just the counting index. So it will look like this in general. C naught plus c1x plus c2x squared plus blah 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 plus cn x to the n plus cn plus 1 x to the n plus 1, and this continues on indefinitely. This continues on forever. More generally, if instead of x to the k, we may also write this as x minus a to the k. And it's basically the same exact thing. So, yeah, where c to the k terms are constants, a is considered the center of the series. This is similar to what we learned in the Taylor polynomial section. And this is called a power series because it contains powers of x or x minus a. And that's why it is called a power series. So, for example, all of the following down here are power series. Let's go ahead and take a second and try to identify what CK, A, what CK and A are for each of these. So for this first one, CK, it's basically everything except for that x to the k term. So in this case, it is 1 over k factorial. And then a, for this example, is 0, because a is the number that we subtract from x when we raise it to the k power. All right, for this guy, for the second example, ck is 1 over 2k, and a is equal to 2, because that's what we subtract from x when we raise it to the k power. And over here in the third example, ck is negative 1 to the k times k, and a is equal to 5. So these are all examples of power series. So something that would not be a power series would be something along the lines of the sum from k equals 0 to infinity of, let's say, k times x minus 2. That would not be a power series. And the reason that's not a power series is because we don't have a k as the exponent of x minus 2. Alright, so that's the definition of a power series. Now let's start to study these objects a little bit more to try and get a sense of why they're useful and what we can do with them. So the first question that you might ask is, when do power series converge? So remember what it means for a series to converge. That basically means that the sum is a finite number. So the infinite sum of terms, Jesus, is finite. Okay. So suppose that we have the object, sum from k equals 0 to infinity, of ck times x minus a to the k. So the idea here is that power series may converge for some values of x, but diverge for other values of x. The values of x for which the power series converge are called the interval of convergence. Pretty intuitive name. And that interval of convergence is denoted by I. The center of the series occurs at x equals a. We'll show a picture of that in a second. And the radius of convergence denoted by r, capital R, is the distance from the center to the boundary of the interval of convergence. All right, so for a quick example, we're going to identify A, I, R for this series down here. All right, so the center of the series, A, occurs at 0 here. And the reason for that is because we essentially have x minus 0 to the k, right? The interval of convergence. So this one we should think about for a second. For which values does this series converge? Well, if we just look back at the first slide that we did, we decided that this series converges when the absolute value of x is less than 1. If it were greater than or equal to 1, then it would diverge. And so the interval of convergence, the values of x for which this series is finite, is -1 to +1 with parentheses on both sides. And the radius of convergence, let's read the definition again, is the distance from the center to the boundary of the interval of convergence. So the center is 0. The boundary of the interval of convergence is 1, or negative 1. The distance from 0 to 1, or the distance from 0 to negative 1, is just 1. So over here on the right, we have a picture that might help explain what's happening here. If the center of the series occurs at 0, and the interval of convergence goes from negative 1 to positive 1, then the radius of convergence is just half of the distance of the interval of convergence. See that? It is either this distance or it is this distance. Either one. That's the radius. Alright, let me erase that because that looks confusing. Okay. So those are the key definitions to know here. So here's the formal theorem from the textbook. And I'll just read it along with you guys. A power series from k equals 0 to infinity of ck times x minus a to the k, centered at a, converges in one of three ways. All right, so this is a little bit different of a concept that we haven't quite talked about yet. So the idea here is that power series will converge in one of three ways. Case 1. The series converges absolutely for all x. So that means that no matter what x you throw into there, it will be a finite value when you plug it into the series. So if it converges absolutely, then by theorem 10.19, it converges for all x, just regularly. In which case the interval of convergence would be negative infinity to positive infinity, and the radius of convergence would be r equals infinity. Case 2 is that there is a real number r such that the series converges absolutely, and therefore converges excuse me, for the absolute value of x minus a less than r, and diverges for values of x such that the absolute value of x minus a is greater than r, in which case the radius of convergence is r. We'll talk about this case more on the next slide. And the third case is that the series converges only at a, in which case the radius of convergence is r equals 0. Okay. So this theorem, 11.3, says that the interval of convergence is symmetric about the point x equals a. And it says nothing about the endpoints of this interval. So this is really only applicable to case number 2. This is the one with endpoints. So for example, if a was equal to 2, if that were the center of your series, and the radius of convergence was 3, that means this distance here is 3, and this distance here is 3, then our interval of convergence could be one of 4 things. Specifically, it could be negative 1 to 5, including both endpoints. It could be negative 1 to 5, including only the right endpoint. Let me erase that and make that clearer. Negative 1 to 5, including only the right endpoint. It could be negative 1 to 5, including only the left endpoint. Or it could be negative 1 to 5, including neither endpoint. So we don't know what happens at the endpoints using this theorem. So in my opinion, this theorem is stated kind of confusing, so let me restate it in a different way. Let r be the radius of convergence, and let I be the interval of convergence. the convergence of the power series falls into one of three categories. The first category is that the radius is infinite, and so the interval of convergence is infinite. Negative infinity to positive infinity. So if the center of the power series was at 0, or really any number for that matter, and it converged for all values of x, doesn't matter what x you throw in, it would converge, then the radius of convergence would be infinity, and the interval of convergence would be negative infinity to positive infinity. The second case, the one that is the least trivial, that takes a little bit of effort, is the case when 0 is less than r, which is less than infinity. So r is a positive number. So this means that the interval of convergence could be any of the following. The interval of convergence could be a minus r to a plus r, could be a minus r to a plus r, including only the left endpoint, including only the right endpoint, or including none of the endpoints. The picture over here on the right kind of demonstrates what that would look like if the interval of convergence was, or if the radius was 4, and the interval of convergence was -2 to 6, including neither endpoint. So you'll see here that there are open dots for both of those, indicating that in this particular picture, for this particular example, the interval of convergence was an open interval from -2 to 6. And the third possibility is that the radius of convergence is 0. And if that is the case, then it will only converge at A. So if we had this series, this power series of x minus a to the k, what we are essentially saying is that the only time when this yields a finite number is when x is equal to a. That is essentially what I am saying. That is case number 3. So the basic idea here is that you always start off with this power series, and then you have to ask yourself, for which values of x does this thing yield a finite number? And I claim to you that there are only 3 possibilities. All right, so let's explore some examples. We're going to find the radius and the interval of convergence for each of these power series. So anytime you get one of these problems that asks you about the convergence of a power series, you are going to use one of 2 tests. You are either going to use the ratio test or the root test, our favorite tests, because they are very easy. All right, generally the ratio test is the way to go, but sometimes the root test is actually simpler. So let's explore them. So we are going to use the ratio test for this first example. And the reason we use the ratio test is because there is a factorial here. And so that gives us some evidence that we should use the ratio test. So let's give it a shot. We are going to define AK to be x to the k over k factorial. And we are going to define AK plus 1 to be x to the k plus 1 over k plus 1 factorial. All right, so before I continue, what I want you guys to think about, to get some intuition behind what we're doing, is to ask yourself, what numbers can I plug into x that give me a finite sum? For what values of x will this thing converge? And so if I were to tell you, what happens if you plug in x equals 0? Will that thing converge? Will that thing converge or diverge? If I were to give you x equals 100, would that thing converge or diverge? If I were to give you x equals -1, would that thing converge or diverge? All right, so think about this question, and later on we will see what the answer is, and hopefully you had some intuition beforehand that this would be the right answer. Okay, so the ratio test tells us that we are going to define r, little r, to be the limit from as k goes to infinity of ak plus 1 over ak. This is the limit as k approaches infinity of x to the k plus 1, sorry, I need an absolute value here, over k plus 1 factorial times k factorial over x to the k. All right, if we compute this limit, on top, what we really have is x to the k times x over k plus 1 times k factorial. And then over here on the right, we have k factorial over x to the k. And you will notice that some things cancel, as they normally do with the ratio test. So we are left with the limit as k approaches infinity of the absolute value of x over k plus 1. Okay, so here's where it gets a little bit strange. I shouldn't say strange. It's not strange. It's just different than what we have done in the past. In the past, this x wouldn't be here, right? We would have some sort of number. So maybe you would have the sum from k equals 0 to infinity of 2 to the k over k factorial. And you would use the ratio test. And instead of an x right over here, you would have a 2 there. And you would be able to compute that limit. And it would be the limit of 2 over k plus 1. And that limit would obviously be 0. Since this is an x, and x is not k, we can actually pull it outside of this limit. So we could rewrite this like this. We could write this as the absolute value of x. We have to keep that absolute value there because we don't know if x is positive or negative. So we have the limit as k approaches infinity of the absolute value of 1 over k plus 1. Alright, and so now think about what the limit as k approaches infinity of 1 over k plus 1 is. Well, that's just 0. Right? And 0 times anything is 0. And so, what are we able to conclude? Well, remember what we're doing. We're doing the ratio test. And the ratio test tells us that if our answer is less than 1, then it converges absolutely. And in fact, since this answer does not depend on x, it doesn't matter what x I had in here, this thing will always be equal to 0. Which is less than 1. So it always converges absolutely. So the conclusion statement here is that since r equals 0, which is less than 1, the series converges absolutely for all values of x. And so this means that we are in this first case here, where the radius is equal to infinity, and the interval of convergence is equal to negative infinity to infinity. because this converged for all values of x. Didn't matter what x we threw in from the beginning, it would converge for all of them. So this question here at the beginning, it doesn't matter what x I have, it will converge for all of them, because it converges for all values of x. So we will say that the radius of convergence is equal to infinity, and the interval of convergence is equal to negative infinity to positive infinity. Alright, so let's try another one. Now we have to find the radius and the interval of convergence for each power series. This time we have negative 1 to the k times x minus 2 to the k all over 4 to the k. Well, here, notice that everything is raised to the k power, so actually the root test will be preferable. So let's do that. Once again, think about it ahead of time. What values of x do you think this series will converge for? Will it converge for x equals 0? Will it converge for x equals 5? How about x equals 12? Negative 20? So just think about that intuitively before we do this problem and see if you're right. So for the root test, we must define rho to be the kth root. No, we got to do a limit first. It is the limit as k approaches infinity of the kth root of the absolute value of our thing inside the sum. So this negative 1 to the k times x minus 2 to the k all over 4 to the k. Close that absolute value. Okay, so the first thing that happens is that the negative 1 to the k just turns into 1. So this thing is really just 1 because it's inside of an absolute value. And then the kth root and the k powers will actually cancel out. And so we are left with just x minus 2 over 4. So let me use some more color here. Those all cancel. Alright, so the idea with this problem is that there are no k's in it anymore, right? And so whenever we try to evaluate this limit, what we're essentially doing is we are taking the limit as k approaches infinity of a constant, of just c. And hopefully, if you remember from our limit rules, that is just equal to c. And so in this case, we are just left with x minus 2 over 4. Absolute value. We could rewrite this as absolute value of x minus 2 over 4, because we know that 4 is positive, but we don't know if x minus 2 is positive or negative. So that's got to remain in the absolute value. So the question we have to ask ourselves is, for which values of x is this value less than 1? So the question I ask, for which values of x is the absolute value of x minus 2 over 4 less than 1? Alright, and the way that we're going to do that, or the way that we figure that out, is we just set up that inequality and solve for x. So we set rho less than 1, which means that we set absolute value of x minus 2 over 4 less than 1. This implies, if we multiply both sides by 4, that the absolute value of x minus 2 is less than 4. Okay, so at this point, you should be able to identify your radius of convergence. To understand why, let's go back to the theorem. This says, in case number 2, that there is a real number r such that the series converges absolutely, and therefore converges, for x minus a less than r. So here's the key idea. If you ever see this, then whatever this number is here is your radius of convergence. So we just got x minus 2 is less than 4, which means that your radius of convergence should be 4. So this is the radius of convergence. All right, so in order to determine the interval of convergence, what we could do is we could notice that in general, if we have absolute value of x less than a number, let's say, I don't want to use a. Actually, let me write it a little bit differently. Let me use. Let's try this. Okay. If we have the absolute value of y less than z, this means that negative z is less than y, which is less than z. So that's what it means for an absolute value to be less than a number. Okay. So we will use that fact down here. The fact that absolute value of x minus 2 is less than 4 means that negative 4 is less than x minus 2, which is less than positive 4. And if we add 2 to every side, we would get negative 2 is less than x, which is less than 6. And so the interval of convergence, let me use a different color. So the interval of convergence contains the numbers negative 2 to 6. Contains negative 2 to 6. So this does not tell us what happens at negative 2 or negative 6. It might converge, it might diverge. We're not sure yet. So now we have to check the endpoints. So now we must check the endpoints. All right, so back to that original question that I asked you guys. What values of x here do you think would cause this thing to converge? It kind of makes sense that values between negative 2 and 6 will allow this thing to converge. Because if, for example, let's say you plugged in x equals 5, you would then get the series, sum from k equals 0 to infinity, of negative 1 to the k, of 5 minus 2, which is just 3, to the k, all over 4 to the k. And we could rewrite that as the sum from k equals 0 to infinity of negative 3/4 to the k. And it makes sense that this thing converges. And that's because it's a geometric series where r, in this case, is equal to negative 3/4, which is less than, which the absolute value of which is less than 1. And so it makes sense that for x equals 5, the thing converges. But for numbers like x equals 7, you would get 5 over 4, negative 5 over 4, inside this parenthesis, and that would diverge. Okay? So now what we're doing is we're going to check what happens at x equals -2 and x equals -6. So checking endpoints. And this is the point where we're going to have to use all of the series tests that we learned in Chapter 10 to determine if a series converges or diverges. So whatever tools are at our disposal, we're going to use them. So for x equals -2, we will have the sum. So this is just what happens whenever we plug in x equals -2. We have the sum from k equals 0 to infinity of -1 to the k times -2 minus 2 to the k all over 4 to the k. We can simplify this. This is the sum from k equals 0 to infinity of, so we have -1 times -4 all over 4. So this is just 4 over 4 to the k. And of course, this is just the sum from k equals 0 to infinity of 1 to the k. But 1 to the k is just 1. And so let me ask you guys this. Does this thing converge or diverge? Think carefully. A lot of people get this wrong. This thing will diverge. And the reason it diverges is because this sum is not finite. If you were to compute this sum, what you would essentially be doing is adding 1 plus 1 plus 1 plus 1 to itself infinitely many times. And so this diverges, and you can specifically say it diverges by the, what's the word? Divergence test. So to add detail, we have that the limit as k approaches infinity of 1 is equal to 1, which is not 0, and so this series diverges. So that says that -2 is not included in the interval of convergence. So x equals -2 is not included in the interval of convergence. So now let's check x equals 6. This is the sum from k equals 0 to infinity of -1 to the k times 6 minus 2 to the k all over 4 to the k. And if everything is raised to the k power, we can put them all inside the same fraction. And in this case, we have -1 times 4 over 4. So we have -4 over 4 all to the k. This is the sum from k equals 0 to infinity of -1 to the k. And I want you guys to think about this one. Does this converge or diverge? This will diverge as well. It also diverges by the divergence test. We can write the details. Limit as k approaches infinity of -1 to the k. Well, this oscillates forever, so this limit does not exist. That is not equal to 0. And so x equals 6 is also not included in the interval of convergence because it didn't converge. All right, and so the final conclusion here is that since neither endpoint converged, we have that the interval of convergence is -2 to 6 with parentheses on both of those, and the radius of convergence is 4. Okay. Another way to think about the radius of convergence, if on this last slide you weren't able to observe it at this point, let's say you just forgot that that's what it meant for a radius of convergence to be true, the radius of convergence is also just half of the distance of the interval of convergence. So we could say that r is equal to 6 minus -2 all over 2. So that's just 8 over 2, which is 4. It's half the distance of your interval of convergence. So that's an alternative way of thinking about it. IOC, of course, is just interval of convergence. All right, let's do another one. Find the radius and the interval of convergence for each power series. This time we have the sum from k equals 1 to infinity of k factorial times x plus 6 to the k power. So once again, well, actually, this time it's slightly different because we sum from k equals 1 to infinity instead of k equals 0. It makes absolutely no difference whatsoever where we start our sum. So in this case, we start from 1, but that will not change our answer in the least. All right, since this is a factorial, we should use the ratio test. We define AK to be k factorial times x plus 6 to the k power. And AK plus 1 to be k plus 1 factorial times x plus 6 to the k plus 1 power. And once again, I want you guys to think about what values of x cause this thing to converge. Will it converge if x is equal to 5? Will it converge if x is equal to 0? X is equal to -5? X is equal to 6? X is equal to 12? Which values cause it to converge? Try and think logically about that before we do our problem, and that'll hopefully give you some intuition whenever you're doing problems of this sort. All right, so continuing. R is defined to be the limit, as k approaches infinity, of the absolute value of ak plus 1 over ak. And so ak plus 1 is k plus 1 factorial times x plus 6 to the k plus 1 all over ak, which is k factorial times x plus 6 to the k. All right, so hopefully we're getting to the point where we can see how this simplifies ahead of time. In this case, the k plus 1 factorial is just k plus 1 times k factorial, and so that will simplify to just be k plus 1. And then the x plus 6 to the k plus 1 is really just x plus 6 to the k times x plus 6, and so that will just simplify to be x plus 6. And then on the denominator we can write 1 if we want to. Okay, here the x plus 6 has no k's associated with it, so we can pull that outside of the entire limit. We can write this as x plus 6 in absolute value times the limit as k approaches infinity of the absolute value of k plus 1. All right, so what is this limit equal to? So in general, the limit as k approaches infinity of k plus 1, that is equal to infinity, right? But we are also multiplying by x plus 6, absolute value of x plus 6. And in most cases, that thing, well, first of all, we know that it's a non-negative number, so it's either 0 or positive. If it is a positive number, then this entire thing will just be equal to infinity. So it is infinity if x plus 6 is positive. But if x plus 6, the absolute value of x plus 6 is equal to 0, then this entire thing is 0. Yeah, that's the end of the sentence. Alright, so the way to think about this is that this entire thing is infinity if x is not equal to negative 6, and it is 0 if x is equal to negative 6. Right, so does that make sense? If we were to throw in a negative 6 right here, then we would get 0 times the limit as k approaches infinity of k plus 1, and 0 times that thing would just be 0. Alright, so if you are particularly observant, you might notice that what we're essentially doing is we're multiplying 0 times infinity, right? And in general, that's an indeterminate form. But the reason that this is not an indeterminate form, the reason why we can definitively say that this case is equal to 0, is because the 0 that we come up with is outside of the limit. So in general, if you were to have something like the limit as k approaches infinity of 1 over k times e to the k, this is also a 0 times infinity sort of case, but this is where both of the terms 0 and infinity are inside of the limit. And in this case, they are not both inside the limit, which is why we can definitively say that it's equal to 0. Alright, so the bottom line here is that this series only converges, let me use a different color, only converges if x is equal to negative 6. Alright, and so that falls into case number 3 that we discussed back in this theorem, where if it only converges at one value, then the radius of convergence is 0, and the interval of convergence is just the number that it converged at. So in this case, r is equal to 0, and the interval of convergence is equal to negative 6. And we will expect you guys to write it in these little curly braces. That indicates a set, the set of numbers that includes only negative 6. Alright, so yeah, that's an example of the third case. So now let's do another one. We're going to find the radius and the interval of convergence for this power series, k equals 1 to infinity, of x minus 2 to the k over the square root of k. So let's give it a shot. We can use either the ratio or the root test here. I think personally that the ratio test is easier, so let's roll with that. reason that the root test would not be useful, well, it would work. The reason that the root test might be a little bit more difficult is because the denominator is not raised to the k power. And that gives us a little bit of difficulty when we're computing the limit. All right, so let's define ak to be x minus 2 to the k power all over the square root of k, and ak plus 1 is equal to x minus 2 to the k plus 1 all over the square root of k plus 1. We define r to be the limit as k approaches infinity of the absolute value of ak plus 1 all over ak, which is equal to the limit as k approaches infinity, absolute value of x minus 2 to the k plus 1 all over the square root of k plus 1 times square root of k all over x minus 2 to the k. Alright, so x minus 2 to the k plus 1 is really just x minus 2 to the k times x minus 2. So that will simplify. We can write this as the limit as k approaches infinity of x minus 2 times square root k all over square root k plus 1. Alright, we can pull that x minus 2 outside of the limit. Once again, still an absolute value. And we get the limit as k approaches infinity of the square root of k all over the square root of k plus 1. Alright, so let's ask ourselves, what is that limit equal to? Well, that limit's equal to 1. And so we are just left with absolute value of x minus 2. Alright, so here, for which values of x does this thing converge? Well, this thing will converge whenever x minus 2 is less than 1. So the series will converge when absolute value of x minus 2 is less than 1. So let's set that up. And figure out what the interval of convergence should be. So first of all, you might notice that the radius of convergence is 1, since we have x minus a less than a number. If we were to continue in this path, we would get that negative 1 is less than x minus 2, which is less than 1. If we now add 2 to every side, we would get 1 less than x, which is less than 3. And so the interval of convergence contains 1 to 3, so we check the endpoints. Alright, we're going to do that on the next slide. So, first endpoint is x equals 1. If we were to throw this into our series, we get the sum from k equals 1 to infinity of 1 minus 2 to the k all over the square root of k. This, of course, is just the sum from k equals 1 to infinity of negative 1 to the k over square root of k. And now we use whatever tools are at our disposal from Chapter 10 to determine whether this series converges or diverges. All right, so the tool that is at our disposal at this point, or that is most reasonable to use, is the alternating series test. So let's use the alternating series test. Huh. Let's define bk, since we already defined ak earlier. We're going to define bk to be 1 over the square root of k. And so we have to ask ourselves, is this series non-increasing, and is its limit equal to 0? So, is bk non-increasing? To test this, what we need to show is that either the derivative of it is less than 0, or we can show that ak plus 1 is bk plus 1 is less than bk. Let's do the latter. Let's show that bk plus 1 is less than bk. Okay? So, we know that k minus 1 is clearly less than k. This implies that the square root of k minus 1 is less than, let me say less than or equal to. And that implies that if we were to invert both sides, 1 over the square root of k minus 1 is greater than or equal to 1 over square root k. And so this is, oh no, I did this wrong. It still is essentially the same thing. Let me restart so that way I don't confuse you guys. Sorry. We know that k plus 1 is greater than or equal to k. This implies that the square root of k plus 1 is greater than or equal to the square root of k. And this implies, if we invert both sides, that 1 over the square root of k plus 1 is less than or equal to 1 over the square root of k. And this is bk plus 1, and this is bk. So what we have essentially shown is that bk plus 1 is less than or equal to bk. So yes, it is indeed non-increasing. All right, the other thing we have to show is that the limit is equal to 0. And indeed it is, because the limit as k approaches infinity of 1 over square root k is just 0. Yes. And so, at x equals 1, the series converges. So by the AST, the series, sum from k equals 1 to infinity, of negative 1 to the k over square root k converges. So x equals 1 is included in the interval of convergence. Okay, kind of running a little bit low on space, but hopefully we can get the second one pretty quickly. All right, so the next one, we have to test what happens at x equals 3 Alright, so we have the sum from k equals 1 to infinity of 3 minus 2 to the k, all over square root k. 3 minus 2 is 1, and then 1 to the k is just 1. So we can rewrite this as the sum from k equals 1 to infinity of 1 over root k. Alright, let me ask you guys, does this thing converge or diverge? This one will diverge because it is a p-series where p is equal to 1/2 is less than 1. So, this diverges by p-series. P equals 1/2, which is less than or equal to 1. So, x equals 3 is not in the interval of convergence. So, in conclusion, after we've tested our endpoints, the idea is that the interval of convergence is equal to 1 to 3, where 1 is included, 3 is not, and the radius of convergence is half of that distance, so 3 minus 1 over 2 is just 1. Whew, lots of examples there. Hopefully these were instructive. This sort of question always appears as a free response question on our exams, so make sure you know how to do this sort of thing. Okay, so I'm going to go ahead and end the video here, and we will continue with part 2 in the next video.